Okay, hello everyone. We are happy to have Marc Williams with us here. Marc is a lecturer or an assistant professor in theoretical computer science at the University of Auckland in New Zealand. His research interests are in computational complexity, particularly proof complexity, which is some of the things he'll be talking about today, and the theory of satisfiability solving, which is like 3SAT. Previously, he did his PhD from the KTH Royal Institute of Technology in Sweden with Jakob Nordstrom. And he did two postdocs, the first one at Tata Institute of Fundamental Research in Mumbai in India, and the second one at the Technion in Haifa in Israel. In TIFR, he was hosted by Professor Alkadev, and in Israel, he was hosted by Professor Yuval. And after that, he was a docent at the St. Petersburg State University in Russia, and also a visitor at the Memorial University of Newfoundland. Okay. So how I know Marc is that while he was doing his postdoc at TIFR, I was doing my PhD there. And then when he went to Israel, I followed him there and we shared an apartment. So over to you, Marc. Thanks.
Yeah, thanks a lot. Yeah, so let's start. Oops. Yeah, so I'll talk about how do we understand algorithms through proofs. And the reason for this is that, well, it's very fascinating how there are some algorithms that do really well, but we have no idea why they're so good. So we have some heuristic algorithms that can solve satisfiability problems with millions of variables in seconds, and the theory says this should be possible. We have AI doing great things that we have no idea what they're doing and how they're being so good. And well, we would like to understand how these algorithms are so good. Turns out that one way to do that is through proofs. So let's start by talking about proofs. Okay, let's start with a problem that's quite interesting, kidney exchange. And the problem here is that we have a few people who need a kidney transplant, and we have some other people who are willing to give a kidney. But the problem is that in real world, sometimes you are not compatible. So you would like to give a kidney to one person, but you cannot do that because of medical reasons. And then a very interesting idea is that you can start finding a group of people who would like to give a kidney and a group of people who need to receive a kidney and try to match them. So you find for each person who would be possible to get a kidney from, you draw this picture in a graph. Like here we have donors that can give a kidney on the left, people who need to receive a kidney on the right. And now if you find a way to match all of these people, then we're very happy because we can make sure that every person who needs a kidney will receive a kidney. So perfect. In this case, the solution to the problem is yes, there's a way to match these people, and the way to show it is just here's these arrows, and here's what we need to do. Now, sometimes, unfortunately, the answer is no, this is not possible. And so here's a different graph of relations between people who can give a kidney and need to receive one. And we find here that there's two people on the right who need to receive a kidney in blue, but there's only one person on the left that they're compatible with. So there's that person on the left can either give the kidney to the first person or the second person, but there's no way to split it in two. So in this case, we wouldn't be able to find the matching. And it's very interesting that we are able to say why. Because now so not only we know that this is not possible, but we also know that it's not possible because of this specific reason, that these two people are not compatible with anyone else. So then this tells us, maybe we should try to find a person that's compatible with these two people, and we'll make tests that to try to find more other people and so on. So eventually maybe we'll change our picture and end up finding a solution. But we can only do that because we know the reason for why this is not working. Right. So what happened here is that this problem of kidney change, it's just a matching problem. We're trying to match vertices on a graph from the left to the right, and we can formalize this problem using linear programming. So just a few equations. We need to say that every person from the left needs to get at least one kidney. Everyone from the right needs at least one. Everyone from the left can give at most one. And if we see all these constraints, we'll get some linear constraints. And the great thing here is that there's a theorem in linear programming called Farquhar's lemma that says that if you have a solution, great, you have a solution. If you don't have a solution, then you'll find a reason for why there's no solution. That's called the duality theorem, and that's what allows us to find the reason for why this is not working. All right, so this is this idealized world where things are simple, but in the real world, things are not so simple. So still, we might want to have the same problem. So some people want to give a kidney, some people need to receive a kidney. But well, we need to do that in a hospital, so we need to take that in mind. And of course, that's hospitals have some operating rooms, some of which are available or maybe not. And of course, some doctors need to take care of that. They can't all be at the same place at different places at different times. There's going to be transport logistics, so if kidney needs to go from one city to the other, that will make things more complicated. And there's going to be some priority lists, some people who really need things more urgently than others. And this is getting really messy. So in that case, if we manage to find a solution, then we're very happy we found a solution. But it could be that, well, there's no solution and we have absolutely no idea why. Right? As in, we try to satisfy all of these constraints at the same time, it doesn't work. And yeah, what do we do with that? So previously we knew that, okay, we should try to find more kidneys, more donors for these people. But now we are at a complete loss. So then, well, is there anything we could do? And sounds hard because this real world kidney exchange problem is NP hard. And that means that if there's a solution, we can verify it easily. That's what NP means. But when there is no solution, we have no guarantees about that. So we run a computer algorithm, it says, no, there's no solution. We have no idea why that is. Then there's no way that the solution can explain that concisely to us. Never mind how easy it is to find. I mean, we're going to forget about that. Let's say that we have a very fast supercomputer that can do all the calculations. We just care about knowing that the computer is right. Well, then since this problem is NP hard, what makes sense then is to try to study the simplest NP hard problem that we know of, which is called the Boolean satisfiability problem. Right? SAT or 3-SAT, as you might know it. And it's this problem, you get a formula over variables x1 up to xn. These variables can take value 0, 1. And we just have 3 ways to connect these variables. We have AND, we have OR, and we have negation, not. So here's an example of a formula. x1 or x12 and x21 or x22 and x31 or x32 and so on. I'm omitting the ands, so there are ands in linking all these clauses. And if we ask, well, does this formula have a solution? The answer is yes, and I can show that very easily to you. The solution is just this assignment. if we take these variables and set their values to 0 or 1, you now can go and check each of these clauses that all of them are satisfied, and you'll be convinced that there is a solution. Right? That's what it means for the problem to be in NP, that if it has a solution, I can show it to you very easily. Maybe it took me a long time to compute that solution, but you can be convinced easily that there is one. Okay, so that's one formula. What about this other formula? It's same formula as before with one more constraint. So now you can start imagining that maybe this formula does not have a solution. And yeah, indeed, it does not have a solution, but how could I prove that to you? Well, one way would be, let's try all the possible truth value assignments. So let's try setting all the variables to 0, then all the variables to 0 except the last one, which will be 1, then 0, 0, 0, 1, 0, 0, 0, 1, 1, and so on. And here, since there are 6 variables, there's going to be 2 to 6 assignments, that's 32, which is feasible, but as you can see, as soon as we have n variables, that will be too inefficient. So if we have 100 variables, we'll need 2 to the 100 assignments. That there's no way we can do that in time. Well done. A way that we could then certify that this formula does not have solutions is to use the rules of logic. And we'll see how to do that using the resolution rule. In resolution, what we do is take 2 clauses, so variable x31 or x32, variable not x22 or not x32, and these 2 clauses have a variable in common, which is x32. And now we do case analysis. So there's 2 things that could happen. Either variable x32 is true. If it's true, then the first clause is already satisfied. We don't need to care about that. But if x32 equals 1, then the clause on the bottom, not x22 or not x32, that the x32 part will go away, and we'll know that not x22 will have to be true. Right? So if x32 is true, then x22 must be false. Otherwise, the other side of the case analysis would be, what if x32 is false? And that will tell us that in that case, x32, x31 must be true because of the first clause. So we can just say that either the first case happens or the second case happens. And the conclusions that we would get from that is this clause x31 or x22 negated. And a completely syntactical way to do that is take these 2 clauses that share a variable, remove the variable from the clause, and attach everything that remains together. Good. We can do this with this pair of clauses. Now we can take another pair of clauses, for instance, this new clause that we had just derived, x31 or not x22, and another clause that we already had, derive a new clause. Then we can take another pair of clauses, get a new clause, and so on. And if we're lucky at some point, we'll get that one variable, we'll get to know the value of one variable. So now we know that x11 must be false. We keep doing more of these operations. Maybe we'll derive that x11 must be true. And now we have that a variable must be both true and false at the same time. That's impossible, and that finishes our proof. So this was a bit better than just trying to list all assignments, but still a not very happy state of affairs. Because, okay, sure, yes, it's shorter, but we couldn't even fit it in one slide, and this was just 9 clauses. Right? So resolution is nice, but hopefully we can do better. And yes, we can do better. And one way to do that is by using the power of algebra. So we'll use something called cutting planes now, which is a different way to build proofs. And instead of using logic, we'll use geometry. or algebra, same thing. So what we'll do is convert these clauses that are just logical statements into linear inequalities. Let's look at the first clause, x11 or x12. What does that clause mean? Well, it means that one of these variables, either x11 or x12, it must be true. Or in other words, that if we sum the values of these variables, it must be greater than 1. Because if they're both 0, then this is falsified. Otherwise, it is satisfied. So we could just write it in that way. And we can do this for all clauses. So we write x11 plus x12 must be greater than 1. And same everywhere else. That's what we get. And now, well, we can do other operations that are not just this resolution. We can do the usual kind of things that we would do with linear inequalities. For instance, we can add them together. And if we take these three inequalities from the middle, and add them together, what we'll get is this inequality that just appeared. So 2 not x11 plus 2 not x21 plus 2 not x31 greater than 3. And what are other things that we can do with inequalities? We can divide them. So let's divide this inequality by 2. But now, notice what happened. So on the left-hand side, we have an expression that only has integer values. So it only takes integer values. But on the right, we have 3/2, so 1.5. What happens here is that, well, either this sum on the left is greater than 1.5, in which case, since it's an integer, it must be greater than 2, or it's less than 1.5. But in particular, if this inequality is true, then the left-hand side must be greater than 2. So we can, in fact, round up and replace that 3/2 by 2 and get something that's slightly stronger. Good. Now we can take these other three inequalities, add them together, divide, we'll get this inequality. We add everything together and take now the inequalities that have positive coefficients, place them here, and now we sum everything. So take these two long inequalities, add them together, and what we'll get is 6 on the left and 7 on the right. And now this is saying that 6 must be greater than 7. That's a contradiction. So that tells us that our original formula does not have any solutions. So if there was one, then this transformation didn't remove any solutions, and all the operations that we did were sound. So that tells us there was no solution here. Awesome. So we have improved a bit. We started with having to enumerate all solutions. Then we had that the resolution was a bit better. And now we have a proof that just fits in one slide. So nice. So starting with the same formula, we saw that there are different ways of trying to prove that there's no solution to it. And well, this is what the field of proof complexity is about. It's just trying to answer the question, how hard is it to prove that a formula, CNF formula that has variables, ands, ors, and negations does not have any solution? And as we saw, that depends on which proof rules we allow. And there's a pretty rich theory. And well, this starts because if you could show that there is some formula that does not have short proofs at all, then you would prove that P is different from NP. So that's how the whole field started. People were trying to prove P different from NP, and this would be a way to do that. And well, even though we've been working on the problem for about 50 years, we are not closer to a solution. But the good thing is that what we have learned about proofs allows us to talk about algorithms. So we can use proofs to we can study concrete proof systems, so such as this resolution proof system or this cutting planes proof system that I mentioned. And then what we understand from these proof systems can be used for algorithm analysis. Right, so how do we do that? Well, let's talk about algorithms to answer this question. Let's start with a well-known algorithm, the DPLL algorithm from the 60s. I think it's from 62 even. And it's the earliest algorithm that we know to find whether a formula is satisfiable or not. And it's a fairly simple algorithm. It's a backtracking algorithm. And what we do is we start with a formula and we give a partial assignment of values to variables in memory. So maybe we remember that variable x must be 0, and that's our state. And what the algorithm does is the following. It looks at which values have been assigned so far and assigns those values to a formula. If we reach a conflict, meaning that there's some part of the formula that's broken by that assignment, that is unsatisfiable, then we realize that, oh, that's not a good assignment, so we backtrack. We change the value of the last variable that we assigned. If at some point there's a unit clause, that's a clause that has only one variable, that means that that variable must be set to that value. Otherwise, we would be immediately falsifying that part of the formula. So then there's no point in branching, in testing the two values. We can just fix on that and go down that branch immediately. And otherwise, there's no fixed value. So what we do is take a variable, doesn't matter which, try setting it to 0. If it works, great. If it doesn't work, then we'll set it to 1 and see if we can find an assignment in that way. So let's see an example of running DPLL on this formula in gray on top. So formula is y or z, y or not z, x or not y or z, x or not y or not z, and not x or not y. If we run the DPLL on this formula, we'll start by looking, well, is there some conflict? No conflict immediately. Is there some clause that is unit? No, all clauses have at least 2 literals. So then what we do is pick one of the variables and branch on it. Let's say that we branch on variable x. Why not? We'll start by setting x equals 0. And then what happens is that all the clauses that contain x, such as the third and fourth clauses, they lose x, so x is not there anymore. While clauses that contain not x, such as the fifth clause, now this clause is satisfied, so we don't have to worry about it anymore. Now it's satisfied, that's fine. And let's look at the formula again. Now all of the remaining clauses, so there's only 4 clauses now, and all of them have exactly 2 literals because x has been removed from the last 2 ones. But still there's no clause that's unit, so there's nothing that the algorithm does. We just go on branch. So we branch on y, and let's start by setting y to 0. What happens now? Well, there were 2 clauses that contained not y. Those clauses are now satisfied, but now the clauses that remain are the 2 first ones, and y has been removed from those. So now we have 2 unit clauses. One that says that z must be true, and another one that says that z must be false. So since a clause tells us that z must be false, we're going to do unit propagation. And now that will lead us to a conflict. Because if we set z to false, then the first clause, y or z, we have set both y to false and z to false. So that's a conflict, meaning that we go back to the last value. So we retract our guess that z must be 0, and we try to set z to 1 instead. But if we set z to 1, then we'll reach a conflict with another clause, y or not z. So in that case, that means that we need to backtrack even more and change the value of y. And even if we change the value of y, then we'll see that again we'll reach conflicts no matter how we set z. So we need to backtrack even more to x. But even in that case, if we try to setting y both to 0 or to 1, neither of those is going to be possible. And we will end up finding that this didn't work. So no matter in which way we set x, y, and z, there's not going to be any solution to this formula. And what we got after running this algorithm is this nice decision tree that at every step of the algorithm, it's telling us which variable do we assign to which value and where did we get conflicts from and so on. So that's pretty nice. We get a search tree. And it's something that we could ask the algorithm to be printing or something that will be generating implicitly as the algorithm runs. It's going to be making all these queries internally. So we could think that every step that the algorithm makes is moving somewhere in this search tree. Okay, that was the DPLL algorithm, classical algorithm. Now, what's the relation between DPLL and these proof systems, these proofs that we are talking about? Turns out that there's a very close relation between DPLL and resolution. So recall that resolution is this rule where we have two clauses that share a variable, and what we do is take the parts that don't have that variable and stitch them together. We can take this search tree from DPLL and transform it into a proof in a very simple way. We just need to go and flip the values of the arrows. And now when we have two clauses that point into the same place, what that means is that you should do a resolution step. So we have clauses y or z and y or not z. They go to the same place. That means that we should resolve over the common variable, which is z. And what we'll get is y or y, which is just 1y. And by the way, it's not a coincidence that z is the same variable that had been queried there. And it will also happen that the query variable is the resolution variable, if you call it that way. So that's pretty amazing then. We had an algorithm, DPLL, and that algorithm immediately gave us a proof. We could ask what happens in the other direction. So if we have a proof, can we transform it into a DPLL run just by flipping the arrows again? And yeah, it turns out that in this case, it's mostly true that if you start with resolution proof, you'll get DPLL, but there are some caveats that we'll see in due time. Anyway, this relation between DPLL and resolution turns out it's not exclusive to DPLL. DPLL is very nice because it's about the SAT problem and it's very clean. But this is actually something that happens for many algorithms. So many algorithms, when you run them, they're going to produce a proof implicitly, just by they will produce some kind of log or transcript. So just by recording which steps the algorithm is taking at every time, you can then use that to reconstruct proof of what the algorithm did. So it would be like this: the algorithm gets an input and it produces an output, but not only that, it also produces this transcript of steps that it produced. And then from that transcript, might not be too clear, but more often than not, we are able to decode that into some kind of proof that makes sense and uses well-defined rules, such as the resolution rule or the cutting planes rule. And now you might be asking, yeah, okay, that's nice. We can get a proof from an algorithm, but why are we doing that? I mean, why don't we look at the algorithm directly and forget about proofs? Well, there are a few advantages to proofs. Basically, proofs are static objects, while algorithms are dynamic and they can be very complicated. So the algorithm might be using very complicated heuristics, being very smart, but the proof is just a list of lines. It's just line 1 is this, line 2 is that, line 3 is that. So there are no heuristics in the proof. It's just what the algorithm did. We don't care why the algorithm did things, we just care about what it did. And since it is a static object, it's way easier to analyze. And one thing that we can gather from proofs is that imagine that you have a formula and you know that it doesn't have any short proofs in a particular proof system. Then if you have an algorithm that produces proofs in that proof system, well, that tells us that there's no way that algorithm can produce a short proof because a short proof does not exist. Right? So then that means that the algorithm must have produced a very long proof. But since every line of the proof corresponds to one step of the algorithm, that means that the algorithm had to do a lot of steps to produce that proof, meaning that it had to run for a very long time. Right? So just by looking at proofs, and if we find that the proof needs to be very long, that tells us that an algorithm will need to take a lot of time to solve a problem. And yeah, as I mentioned, one example of that is the SAT problem and the DPL algorithm. And it's a very classic example because SAT is a logical language, so it makes a lot of sense that you would use logic to solve SAT. But there are quite a few problems where we have this translation. So for instance, there are pseudo-Boolean or integer programming problems where the algorithms correspond to cutting planes or another version of that called stopping planes. And again, it's not a big surprise because we know that these are doing geometric reasoning. So of course you would expect to have rules working with linear inequalities. But then there are some other problems such as finding cliques or algorithm for graph coloring, where there are some algorithms, and it turns out that if you look at what they're doing, you can extract proof in this resolution format or a format called polynomial calculus that I did not talk about. But yeah, even if the algorithm is not using logic itself, if you think hard enough, it turns out that it actually is. And then you can study the proof that they produce and find cases where the algorithm doesn't perform so well. Great. So now I want to continue talking about this DPLL algorithm, and I'll talk about the cousin of DPLL that is called CDCL. It's the better and improved version of DPLL. And it's actually what is being used in practice. So DPLL is an algorithm from the 60s. CDCL is an algorithm from late 90s, I think 97. And it's one of these algorithms that's very surprising. So I mentioned that there are some algorithms that are solving formulas with million variables, and CDCL is such algorithm. It uses heuristics that are not that complicated to explain, but are complicated to understand. And really, the only way we have to understand CDCL is using proofs. In DPLL, it's backtracking. There's tools to understand DPLL outside of proofs, but CDCL, we really have no better idea than proofs. Okay, but so what is CDCL? Recall what DPLL did. It was this backtracking algorithm. It just does, if there's a conflict, we're going to backtrack. If there's a unit clause, we're going to unit propagate. If else, then we'll take a variable and try both values. Now in CDCL, what we do is if there's a conflict, we're not only going to backtrack, but we're going to learn the reason for that conflict. Let me explain that. Here in this DPLL tree, remember that we found our first conflict when we tried setting x to 0, y to 0, and then z to first to 0 and to 1, so that neither variable was possible. So we found that we had to backtrack z. If we think about it, the reason why we couldn't set z to 0 or to 1 was because of the first two clauses, so y or z and y or not z. If you notice, there's no mention to x in these clauses. So it didn't matter that we had set x to 0 at the beginning. So what we could learn from this conflict, if we are naive and using DPLL, is that you shouldn't set x to 0 and y to 0 at the same time. But being a bit smarter, we can figure out that actually x didn't matter. The only important thing is that you should never set y to 0. If you do that, you'll never be able to find a solution. And now this can be useful the next time that, so we're branching on x, but now and setting it to 0. But now when we branch on x and set it to 1, maybe we will be tempted to set y to 0 again. But now we know that this is something that we should not do. And this will allow us to cut part of the search tree and save some calculations. So that seems useful. I mean, we're saving some to do some calculations again and again, but how useful is that? Well, to answer this question, we'll use proof complexity. That's not a surprise by now. First, let's see how do we think of CDCL as a proof. And the idea is going to be exactly the same as DPLL. So here's the search tree from CDCL, except that now there's going to be some place in the search tree where we are cutting part of the search tree, not because of one of the original clauses, but because of one of the clauses that we have learned. That is, so here we have a clause that's just y. This is not one of our original clauses, it's just a learn clause. So it wouldn't be right to use that in a proof because it's not an original clause. So how could we fix that? Well, the good news is that if we're using a clause somewhere and it's not in the proof, that means that we had used it previously. So all that we have to do is find where did that clause appear and now draw another arrow from that clause to where we are using it. Now our proof will no longer look like a tree, it will actually look like a more complex directed acyclic graph, where there are going to be some clauses that are used not just once, but multiple times. So seems like an innocent enough difference. So DPLL, from DPLL we got a proof that looked like a tree. From resolution CDCL we get a proof that does not look like a tree. Is that important? Well, yes, turns out it's very important. Because we know from the proof complexity literature that there are some formulas that have short proofs in resolution, but that's only in general resolution. So if you try to build a proof that looks like a tree for that formula, it will need to be exponentially long. So then let me just repeat that. There are formulas, they have polynomial size, they have polynomial length resolution proof, but every resolution proof that looks like a tree is exponential. So now this tells us that if we take this formula and run CDCL on it, in principle, because there's a polynomial proof, there's no reason why it should fail. While for DPLL, we know theoretically that no matter how smart we choose the heuristics for DPLL, there's no sure proof. So DPLL on that formula will need to run for an exponential number of steps. And yeah, so that explains partially why CDCL was such a big change. So in 35 years, DPL had not changed much. It was improving, but slowly. And suddenly, people thought about of this learning idea, and bam, CDCL was suddenly very fast. And yeah, that's one of the reasons that DPL was stuck trying to find proofs that did not exist. And with CDCL, we got extra reasoning power, and that's why it works that well. Yeah, but the next question anyway is, we have CDCL, we know it's not constrained by this tree-like constraint, but maybe that's not buying as much. Maybe it still doesn't have the full power of resolution, and there are some formulas that have short resolution proofs, but still CDCL is not good enough. Right? So then the question is, if you have a formula with a short resolution proof, can you always find a short proof in CDCL? And well, this is something that started being investigated in shortly after CDCL was presented. And finally, the question was essentially settled, showing that CDCL is as powerful as resolution. If you have a short resolution proof, then CDCL will be able to find it in polynomial time. And that's not completely true. It's not true that CDCL will find it. It means that if you give it enough hints, so if you choose optimal heuristics, then CDCL will find it. But actually, you can also show that there are some other formulas that have short proofs, but where if you use normal heuristics, then CDCL will fail. And there's even a very nice paper saying that if you always were able to find short proofs with CDCL when they exist, then P would be equal to NP. So we actually think that it's not possible for CDCL to find short resolution proofs in all cases. But then that's a question of a proof existing versus finding it, and let's not go in that deep. We'll just say that sure, CDCL and resolution are roughly equivalent. And as I said, that's one reason why CDCL is this great algorithm that's working so well in the real world. Great. Then that's what's been done so far, but the future, CDCL might be great, but it still has some very stupid limitations. For instance, if you try to solve a problem like the pigeonhole principle, you say that we have 10 pigeons that should go into 9 holes. A human will immediately tell you, no, that's impossible. That doesn't have a solution. CDCL will still do that. But now if you tell it, okay, now have 20 pigeons and 19 holes, and CDCL will start thinking and thinking and thinking, and it will not finish. And that's not because CDCL is a stupid algorithm, it's actually because resolution is a stupid proof system. It cannot count. But not all is lost. We saw at the beginning of the talk a proof system that could count, which was the cutting planes proof system. Right? That was this proof system where instead of working with logical rules, we worked with linear inequalities. And so could we perhaps use this proof system to build better algorithms for satisfiability? And this is an emerging area. These are called pseudo-Boolean solving algorithms. I mean, it's not really that new. I mean, this has been studied since the 80s, actually, but there have been some successes recently, and they are somewhat related to proof complexity. And what I would say is that SAT, yes, we can improve CTCL as much as we want, but if we want to do better than resolution, then of course we need to do other things. Anyway, this is the kind of problem that we're trying to solve now. So instead of SAT, we just go and translate that problem into linear inequalities. So x1 or x2, that's now translated into x1 plus x2 greater than 1. And our problems are going to look like this, with some linear inequalities that also and they're over variables that take value 0, 1. And here I'm also having coefficients just 1 for the variables, but in principle it could be okay to have, for instance, something like 2x1 1 plus 3x1 2 greater or equal than 4. That's also a reasonable constraint. But since we're thinking about formulas that come from SAT, in that case, we just have variables with coefficient 1. And really the problem is exactly the same as with SAT. We want to know if a system of linear inequalities over the integers and over 0, 1 in particular, do they have a solution or not? And if we want to do this algorithmically, then that's where these pseudo-Boolean solver algorithms come up. And there are some cases where they do really well. And one example is these pigeonhole formulas. But to be fair, in many industrial cases, CDCL is still better. And that's a bit surprising because these pseudo-Boolean algorithms are using the cutting planes proof system internally. So what they're doing is taking their formula and translate it into these linear inequalities. That gives more power over resolution. So in fact, we know that there are some formulas where cutting planes is exponentially better than resolution is. And yeah, in that formula, for those formulas, the pseudo-Boolean algorithms should do better, but it's not that good. Okay, so let's then discuss a bit what these algorithms do and what proof complexity has to say about that. So when I mentioned, when I explained cutting planes, I explained that one operation that we could do was take take a linear inequality and divide it by 2 and then round up, right? So for instance, here we have an inequality saying 5x1 plus 3x2 plus 2x3 greater than 3. We can divide by 2 and we'll get 5 halves, 3 halves, 1 and 1.5 on the right. And now we can just go and round up and we'll get 3, 2, 1 and 2. And that's a stronger inequality than we had started with. So that is something that would not be true if variables were real, but it's something that's fine to do when variables are 0, 1. And this is called the division rule. There's another way to do that, to use that information, which is called the saturation rule. And it does the following. So it takes linear inequality, like 5x1 plus 3x2 plus 2x3 greater than 3. And now it thinks, well, this variable 5x1, if I set it to 1, I'll already get a 5 directly. And then I'll get 5 greater than 3, and that will be true. But I would get exactly the same result if I had the 3, because if x1 is 0, then it doesn't matter which number is multiplying it, because anything times 0 is 0. And if I set it to 1 and it's 3, then 3 is already greater than 3. So having a 5 there was overkill. So let me just go and replace that 5 by a 3. Why not? And again, this is something that makes sense when you have 0, 1 values. It does not make sense when you have real numbers. And yeah, this is really necessary if you want your proof system to be complete. So if you have a formula that has linear inequalities and you only do addition, you will not find that it doesn't have solutions. But if you add either of these rules, so you add either division or you add saturation, then the proof system will be complete, meaning that every formula that does not have a solution will have a proof. And these two rules, well, one of them is used in theory, division, and another one, saturation, is more used in practice. So the question then is, are these rules equivalent? And why is it that one is only used in theory while the other is used in practice? Turns out that this saturation rule is a very bad idea. So what pseudo-Boolean algorithms used to use in practice, the saturation rule, it just goes back to resolution. So cutting planes with saturation, it gives you no additional power in front of resolution. That means that you have built an algorithm, a solver, that uses linear inequalities. It's doing some very complex reasoning, very smart things, but it's not giving it any extra power on top of CDCL. So then you could think, well, what if I give division to cutting planes? And yeah, then there are formulas where cutting planes with division is much better than with saturation. And that's one reason why the standard pseudo-Boolean solvers were not very good. And the next obvious thing is, well, let's then take a pseudo-Boolean solver and add the division rule to it. Will it work? And yeah, it works actually pretty well. And nowadays, it's standard for algorithms that use pseudo-Boolean reasoning to have the division rule on top of saturation. I mean, there are still cases where you want to do saturation, but using division is very important. And in fact, this is an open problem in the sense that there's many different ways in which you could do division, and deciding when to do division and what to divide and which coefficients and all that. It's a very tricky problem, and yeah, there are heuristics to that, and it's a problem that we're investigating nowadays and trying to figure out what's the best way to implement the cutting planes proof system using a pseudo-Boolean algorithm. Anyway, let me conclude. What I showed is that we can explain algorithms, why they work, why they don't work using proofs. So when there's long proofs, the algorithm cannot work. When there's short proofs, maybe there's hope for the algorithm to work. And by looking at that, well, we could figure out that it was a good idea to use division, and we could improve the pseudo-Boolean algorithms to use division and make them work better in practice. So what's next? What can we do next? There's the question of trying to understand heuristics. As in, I mentioned that for CDCL, for instance, even if there was a short proof, that didn't mean that the algorithm could find it. So can we understand the heuristics better? And that will require, well, probably not looking only at proofs, but also looking a bit at the algorithms. Then there's the question of polynomial factors, meaning that if you have a short proof, but the proof has a polynomial n to the 10, that doesn't mean much. It's not really that good. So even if a proof is polynomial, what matters is that the polynomial should be small, something like n or n squared, but not much more than that. Yeah, so then can we look at how algorithms simulate proof systems in a more careful way and find out, are they simulating them exactly, or is there some overhead in the simulation? And there's the question of looking at more algorithms. So I had that table with many different problems and algorithms and proofs and corresponding to them. I talked a bit about CTCL and pseudo-Boolean solving, but there's plenty of more problems that we should be able to study better using proofs. And probably the next one is integer programming, but plenty of problems to look at. And that's everything from me.
Okay, thanks for that nice talk, Mark. Anyone has any questions? Yeah, please unmute yourself and ask the question if you haven't. So Mark, I have a question. So
Mhm.
when you went through the resolution, the very first one, um, in that it took linear time, right? Like because for each one you will just check, and once you get you end up with a contradiction, you stop. So it doesn't that work in linear time?
So let's go back. I think this was slide not 3.
Yeah, here.
Here, right? Right. So in this example, actually, this takes time 2 to the square root of n.
But why? I mean, because you're going through. Um,
Yeah. What will happen is that this is very small example, so it's 2 sat and it's not that hard. But um,
okay.
so it's not true that you can just take one one of the new clauses and one of the old
Okay,
clauses,
I see.
resolve them together, and so on, and do this linear
Yeah,
thing.
yeah, yeah. Okay, I see, I see.
You'll have to actually do many combinations of new clauses, and it will not be as simple as this linear thing. It will actually look like a very complex tree with many branches.
That's
Yeah,
right.
this example looks a bit misleading because it looks linear, but it's actually not.
Okay, okay. And for the next, so this is 2 to the root n, and for the next one, which was the algebraic
Yeah,
one.
this one is polynomial. I think linear or quadratic.
Okay, okay, I see. Okay, so uh, if there is a single 3-sat expression for which you can prove that every proof takes exponential time, then P is not equal to NP, right? Is
Yeah,
that true?
that's right. That's this point. Yeah.
Oh, yeah. So my question was, is it true the other way also? Um, that
That if P different from NP, then some formula doesn't have any short proofs.
um, yeah. Okay, that
Um,
is 1 second.
no, I think this
Oh
should
no.
not
No,
be
no. Then
true
you would have to
because
prove. Yeah, I think what would happen is then you would have to prove that every you would have to look at every 3-sat expression and
so what you would get, this some formula has no short proofs,
Mhm.
is basically saying is NP equals co-NP.
Mhm.
So it could be that P is different from NP, but still NP equals co-NP, which no one believes that, right? But it could happen.
Mhm. I see.
While if NP is different from co-NP, then in particular P is different from NP because
Yeah,
P and co-P are the same.
that's right. So if right, okay. So yeah, so back to the earlier question. So if you have a 3-sat expression for which every proof is exponential in length, then P is not equal to NP. So
Mhm.
Do we have a good candidate 3-sat or 3CNF expression for which people believe that every proof should be exponential?
Yes, random formulas.
Oh, you just take a.
So you take a formula at random,
Mhm.
3CNF, and you make sure that the number of clauses is about 4.2 times the number of variables.
Mhm.
So if you have 100 variables, then you would have 423 clauses. And yeah, then we think that that doesn't have short proofs in any proof system. But we also have no clue how one would prove that.
How would you possibly prove that? Yeah.
Yeah.
Hmm. I see. I see.
So we know that these are hard for resolution, for instance, but yeah, we have no idea how you would do it in general.
I see. Okay. Okay. Anyone has any questions? Please unmute yourself and you can ask it directly. Okay, so if there are no more questions, let's thank Mark once more. Yeah,
Great. Thank you.
yeah. Okay, so I'll just stop the recording. Okay.